Good morning. Uh, this is lecture 6. In the previous lecture, we have started our discussion on the reverse Breton or Joule or Bell-Coleman cycle. Okay, and then we also saw that COP of the reverse Breton cycle is given as T1 by T2 minus T1, and it is also expressed in terms of the pressure ratio of the cycle Rp gamma minus 1 by uh, gamma whole minus 1. Okay, and this relation tells us that when we increase the pressure, the COP of the reverse Breton cycle decreases. Okay, now we also made a comparison of the reverse Breton cycle with the Carnot cycle. Okay, so in reverse Breton cycle, basically our all the processes are internally reversible and heat addition and heat rejection is isobaric. On contrary, in case of Carnot cycle, we have isothermal heat addition and isothermal heat rejection, and all the processes are totally reversible. So if we compare the equivalent Carnot cycle, we find that the COP of the reverse Carnot cycle is greater in comparison to COP of the reverse Breton cycle. Now we will start our discussion on the actual Joule or Bell-Coleman or reverse Breton cycle. Okay, so what is the meaning of actual cycle? Basically, whenever we do talk about ideal cycle, then we make certain assumptions. For example, all the processes are internally reversible. Okay, so for internally reversible processes, the losses will be actually completely zero. Okay, for example, during the heat addition process, what happens? Gas moves in the heat exchanger coil. Okay, and in that coil, basically, it transfers the heat to the surroundings. Okay, now whenever a fluid flows through a pipe, because of the finite viscosity of the fluid, because in reality there cannot be any fluid with zero viscosity. Okay, so because of the finite viscosity of the fluid, inside the heat exchanger tubes, when fluid moves, there is actually significant amount of pressure drop. Okay, so in actual processes, there will be pressure drop. The heat addition or heat rejection process cannot be completely isobaric. In the similar way, whenever we do make the assumption of isentropic compression and expansion processes inside the turbine and the compressor, there we assume that there is no entropy generation. However, in actual processes, either because of some amount of heat exchange, because even if you put significant amount of insulation along the body of the compressor or turbine, still there will be actually some heat leakages because insulation cannot be 100% perfect. Okay, and moreover, because of the other issues, for example, again the fluid is flowing across the blades of the turbine. So, because of the finite viscosity of the fluid, there will be relative motion in between the different layers of the fluid and the blade of the turbine. Okay, so that will also causes some amount of irreversibility, and we will be having some entropy generation in different processes. Okay, so if I plot the ideal cycle on the TS diagram, then ideal cycle looks something like this: 1, 2, 3, 4, and 1. So this is the ideal cycle. Okay. Now if I start with the actual cycle, what I will be finding that whenever we are moving from process 1 to 2, the entropy of the working fluid will not remain constant. However, because of the irreversibilities, the amount of entropy will increase, because during the process always there will be generation of the entropy because of irreversibility, and entropy generation term is always greater than equal to 0. It is equal to 0 for a perfectly reversible process, and it is greater than 0 for irreversible process. So because of this, I will be finding that instead of ending at point 2, the process 1 will take different path, and the path will be, as working fluid keeps on moving along the blades of the compressor, its entropy will keep on increasing, and finally we have to reach on this pressure line. So my compression process will be ending somewhere at point 2s. Okay, And whenever we represent the different processes on the thermodynamic cycle, basically the quasi-static or reversible processes are represented with the solid line, and actual processes on the property diagrams are represented with the dashed line. So that's why I am not writing a continuous, I am not drawing a continuous line over here, I am drawing a dashed line. Okay. Now this 2 is exit of compressor. At the exit of compressor we have an isobaric heat exchanger. Okay, but as I told you that in the coils of the heat exchanger, when fluid will be moving, there will be pressure drop. So instead of moving along the constant pressure line, the actual process, in actual process, it will be keep on deviating from the constant pressure line, and it will be having maximum deviation at where maximum deviation will be, because whenever it is moving away along the length of the pipe, pressure drop is keep on increasing. So because of increase in pressure drop, the maximum deviation will be observed at the exit. Okay, so actual point will be somewhere at 3 dash. All are clear with this? Now when 3 dash 2, again I will be having the expansion process. What will be happening? Please tell me. During the expansion process, the point 4 will be moving towards left or towards right? Left or right? Right only, because entropy generation is always positive. Okay, so in a process, if entropy is generating, then it will be moving always in the rightward direction. Now this is point 4 dash. Now you will be surprised to see that whenever I am representing point 4, I have put it slightly below the constant pressure line. Why? Because when it will be moving from 4 dash to 1, I have to complete the cycle. If I have to complete the cycle, I have to again reach to point number 1 only. Okay, but whenever it will be exchanging heat with the refrigerated space, here I will be having some heat exchanger again. So in that heat exchanger also there will be pressure drop. Okay, so because of that pressure drop, sorry, I need to place it slightly above, because inlet pressure should be more than the exit. Is this one clear? So point 4 dash will be slightly above the constant pressure line, so that whatever pressure drop is taking place, actually, so constant pressure line to point 4 dash will be something like this. So from this constant pressure line, actually pressure has decreased. Is this one clear? All are clear with this or not? Anyone is having any doubt? So this is actually the actual refrigeration cycle. So 1, 2, 3, 4 is ideal cycle, and 1, 2 dash, 3 dash and 4 dash is the actual cycle. Okay, so if you have to do the analysis of the actual cycle, majority of the things will be valid with small deviation. What will be deviation? For an isentropic process, work done is H2 minus H1. But in an actual process, work consumed by the condenser, so this is for the isentropic WC iso. But if I calculate WC actual, then WC actual will be equal to nothing but H2 dash minus H1 dash. Okay, so basically I will be having some isentropic efficiency of compressor over here, which is given as the ratio of, what is isentropic efficiency for a compressor? It is the ideal work consumed by the compressor divided by actual work consumed by the compressor. Is this point clear? So ideal work will be H2 minus H1, and actual work will be H2 dash minus H1, not H1 dash H1. Starting point is this one clear? So it means that if it is given to you in the question that isentropic efficiency of compressor is 80%, what you need to do? First, you need to assume a isentropic process. From the isentropic process, you can find out H2 minus H1, and that H2 minus H1, then you must divide with isentropic efficiency of the compressor in order to obtain the actual work supplied to the compressor. Okay, and this actual work supplied to the compressor will also give you the value of enthalpy at point 2 dash, because actual work can be written as H2 dash minus H1 dash. So if you know the value of H2 dash, you can locate exact point. Okay, and this further can be written in terms of Cp into T2 minus T1 based on the air standard assumptions, and Cp into T2 dash minus T1. So from here you can calculate actually the value of T2 dash. Okay, so in a numerical problem, for isentropic process, T2 by T1 will be equal to nothing but P2 by P1 gamma minus 1 by gamma. Okay, but from here, if you know T1 and pressure ratio, then you can calculate the value of T2, and this T2 you can then substitute in the definition of isentropic efficiency to calculate actual exit of the compressor, which is nothing but T2 dash. Is this one here? So it means the analysis of actual cycle is always done in assistance with the ideal cycle. Okay, so we try to first easily analyze the cycle for ideal processes. Okay, and after that deviations we account for by using the isentropic efficiency term. All are clear with this point? Now similarly, I am having process 3 to 4 is isentropic and 3 dash to 4 dash is what? 3 dash to 4 dash is actual process, non-isentropic process. Okay, so isentropic work in the turbine will be how much? H3 minus H4. Actual work in the turbine will be how much? H3 dash minus H4 dash. Now you tell me, what is isentropic efficiency for turbine? For compressor it is ideal work by actual work. For turbine it will be actual work by ideal work. Okay, actual divided by WT ideal. So it means H3 dash minus H4 dash divided by H3 minus H4. Now can you tell me why we reverse this isentropic efficiency as actual by ideal in case of turbine? You have to now note down two important statements. Work consuming device consumes least amount of work during the ideal reversible process, whereas work producing device produces the highest amount of work during the ideal reversible process. It means that during the actual process, work consuming device will be consuming more than the minimum amount of the work. Okay, so that's why actual work of work consuming device will be greater in comparison to work required for ideal process. So in order to maintain the value of efficiency less than 1, the ratio will be ideal work required divided by actual work supplied. Whereas the work producing device will give maximum amount of work during ideal process, and if there is any irreversibility associated, then actual work obtained will be less than the ideal work. So that's why actual divided by maximum possible work defines the efficiency of the work producing device, because for work producing device always our reference to be maximize, our objective to be maximized. We have to increase the work output from a system, okay, in order to get highly efficient system. Whereas for work consuming device, our effort should be to produce a system which consumes the least amount of energy. Is this point clear? Anyone is having any doubt about this? Okay, so of course I will not give further details because this much understanding is sufficient enough for solving the numerical problems. Probably in the next session we will have some lecture cum tutorial session where we will try to solve some numerical problems on air refrigeration cycles. Okay. Now let me give you two ideas that I will be giving you very briefly. I will not discuss in detail. Moreover, these are not even listed in your syllabus as well. So, but just for the sake of completeness, I will introduce two more small topics. Okay. So, we have seen that the COP of a reverse Brayton cycle decreases when the pressure ratio increases, and there will be some value of pressure ratio corresponding to which the COP value will become equal to 0. Okay, so to avoid this issue, one another variant of refrigeration cycle is proposed so that the COP does not become 0 for any arbitrary pressure ratio. Okay, so that variant is called as regenerative reverse Brayton cycle. So regenerative reverse Brayton cycle. So basically what is done in this cycle, you have four processes as it is, one additional heat exchanger is introduced. So first you have isobaric heat rejection, then you have what? After isobaric heat rejection, you have here one heat exchanger. And after this heat exchanger, then you have actually turbine. Okay. Then after the turbine, I have again heat exchanger, and from this, then what we do, what comes out of this heat exchanger, first this we pass through this heat exchanger and then we pass it through a compressor. Is this point clear? All are clear to this point or not? So please tell me now, what is the objective of this heat exchanger? This heat exchanger is used in the refrigerated space, the space which I want to cool, correct? This heat exchanger is used with the ambient because I want to dump the heat to the ambient condition. But there is one additional heat exchanger, and now by following the block diagram, we will try to follow the TS diagram as well, so that the purpose of this heat exchanger is clear to us. Okay, so say on the TS diagram, this is point 1. What will be happening? From point 1 I am doing compression to go to point 2. So isentropic compression to reach to point 2. Then from point 2 to 3 I am doing cooling inside the heat exchanger, which is dumping the heat to the ambient. Okay. So 2 to 3. Again I have a heat exchanger. Now you have to understand one important point. This point 3 is corresponding to the high pressure. Okay. So at high pressure its temperature will be higher, whereas the point which is coming at the exit of the heat exchanger, which is used in the refrigerator, is 0.6, and this point is having low pressure because this point is after the expansion through the turbine. Okay, so of course 0.6 will be having low temperature in comparison to temperature of 0.3. All are agreeing to this point? 0.6 will be having temperature lower in comparison to temperature of 0.3. So it means heat will be transferring in this direction. whatever the stream is coming from point 3, that will transfer heat to the stream which is entering in the opposite side of the heat exchanger at point 6. Okay, so from point 3 I will be doing further cooling in the heat exchanger up to point 4. All are clear with this point? Then 4 to 5 I am doing expansion. Then 5 to 6 I am taking heat in the refrigerated space. So somewhere over here is my point number 6. And 6 to 1 is the heat gained by the working fluid in this additional heat exchanger at the same pressure conditions. Okay, so this is my process 6 to 1. All are clear with this point? So now you can understand that the process number 3 to 4 and 6 to 1, these are simultaneously taking place in this additional heat exchanger. All are clear with this point? So these two processes are simultaneously taking place in this heat exchanger. So this type of cycle is called as regenerative reverse Brayton. Okay, one important point, let me ask, this point 3, up to what maximum limit I can cool? Cooling of point 3 in this heat exchanger can be up to which temperature? Yes, maximum cooling can go up to T6 temperature. Similarly, the heating of 6 to maximum temperature, it can go up to T3. Yes, so point 6 can maximum go up to basically temperature T3 in this heat exchanger. Okay, all are clear with this point? Why these points are important? Later on we will be defining effectiveness of heat exchanger when we will be solving the numerical problems on this idea. So for that purpose we should know these critical limits. All are clear with this? Okay. Now after the regenerative idea, let me discuss the concept of open versus closed air refrigeration cycles. Okay, so do you know the difference between open versus closed power cycles? Have you studied open versus closed power cycles? When you discussed about, say, Brayton power cycle in your thermodynamics or ECD course? So Brayton cycle, I told you, a gas turbine engine. Okay. So in gas turbine engine, what happens? Ambient air enters the compressor, then it high pressure, high temperature air passes through a combustion chamber. Then part of this is expanded over the turbine, and remaining part is expanded over the nozzle, and all the exhaust gases are then dumped into the atmosphere. So it means this process is nothing but so in this process there is no heat rejection process. Basically heat rejection is heat is directly being dumped into the, or hot exhaust gases are directly being dumped into the ambient at the same exit condition, and always intake of air is done at the ambient condition from the atmosphere. So this type of cycle is called as open cycle. Okay. On the other hand, if instead of dumping the exhaust gases to the atmosphere, I collect all these exhaust gases and again passes through a heat exchanger to cool these and bring back their temperature to the initial temperature condition, then my working fluid will not be dumped into the ambient, and working fluid can continuously move through all the components in a closed cyclic manner. Okay, so that is the difference between open cycle and closed cycle. Now, open cycle has some disadvantage. What disadvantage open cycle is having? if you are operating in an open cycle, always you are taking air from ambient. So if you are taking air from ambient condition, it means that inlet of the compressor has to be always at the atmospheric pressure conditions. Are you agreeing to this point? So inlet has to be always at atmospheric pressure. If inlet is always at atmospheric pressure, corresponding to that, the density of the air will be low. So because of low density of air, in order to achieve significant amount of refrigeration effect, you have to use large volume of the air. And for handling large volume of the air, your components will be larger in size. All are clear to this point? On the other hand, if you operate with the closed cycles, in case of closed cycle, like in open cycle, I told you that if this is the TS diagram, this compressor exit always has to be, it always has to be atmospheric, sorry, inlet. But in case of closed cycle, because you are not dumping the gases to ambient, you are operating in a closed manner. So if you are operating in a closed manner, if this pressure can be any pressure greater than or less than atmospheric pressure as per our requirements. Is this one clear? So in a closed cycle, the pressure at the inlet of compressor, it can be either kept greater than the atmospheric pressure or it can be kept less than the atmospheric pressure as per our requirements. All are clear with this point? So when we keep the pressure above than the atmospheric pressure, corresponding to that, density of the air will be increasing. All are clear with this point? So if density of air is increasing, it means for handling the same mass of air, the volume flow rate required will be less. Okay, so it means your size of the components will be smaller for a closed cycle. Another important point is, whenever you are operating in a closed cycle, other than air, you can use any type of gaseous working fluid whose properties are commensurate with our requirements of the refrigeration space. Is this point clear or not? Okay, so instead of always using air, because in an open cycle, from where I have to take the gases? Of course from ambient, and in ambient only gas present is air. Okay, so if I have to operate an open cycle, always I have to operate it using the air. Even for availability, if I create some localized tank, then also some gases I cannot directly dump into the ambient at the exit because of their flammability and other toxic behaviors. Okay, so the closed cycles gives us flexibility that we can operate at any pressure and we can operate using any gas other than the air. Sometimes different gases will be having different temperature and pressure conditions and specific volume conditions which may be suitable for our refrigerated space requirements. Is this one clear? So the idea of open and closed cycles is clear. Now the Brayton cycle is having flexibility. Reverse Brayton cycle is having flexibility. It can operate in both open as well as closed conditions. So this is one feature, and when I am saying that it can operate in both open and closed conditions, of course closed conditions we have already seen, but if I talk about open conditions, it can operate in open conditions both for high pressure heat exchanger or low pressure heat exchanger. Is this point clear? How it can operate in an open condition for low pressure heat exchanger, you can consider it like this. Say this is the room and this room you want to maintain at low temperature condition. Okay, and you want to operate you want to maintain this room using the gas refrigeration cycle. So what you can do, you can take some duct from this room, and this duct will be actually supplying the air, to the room air to the compressor. So this is the room air which is taken by compressor, and of course this room will be at atmospheric pressure conditions. Then you have compressed this room air, and in the heat exchanger you have rejected the heat from the room air, okay, and then you have passed this room air over a turbine. The expansion in the turbine will decrease the temperature of this room air, and then you have one more duct through which you have again circulated the room air to the cooled air to the room again. Okay, so this way, whenever you are operating a air refrigeration cycle, in this is nothing but our atmosphere. Okay, so here we are not using any coil where the same mass of air is again circulated. Okay, because the compressor at a single time it cannot suck all the entire amount of air. It will be taking some fraction of air, and some other volume of air it will be supplying from the other end. It is like this: from this corner it is taking the air, from that corner it is supplying the air. Okay, so same quantity of air is not circulating, but random quantity of air is taken from the room and random quantity of cold air is supplied to the room. So this is one way of operating a open air refrigeration cycle, particularly when low pressure heat exchanger is removed. Is this point clear? So when low pressure heat exchanger is removed, the deviation of this cycle from actual cycle is actually very less. There is not much deviation. Okay, but now if I go with other condition, what could be the other condition? Other condition is, I want to operate the open cycle in such a way so that I want to reject which heat exchanger? High pressure side heat exchanger. All are clear with this idea or not? So if I have to remove high pressure side heat exchanger, then what will be happening? Will the cycle will remain as it is? Because here compressor is supplying the air. Will it remain as it is? No. So whenever you are removing the high pressure side heat exchanger, you have to modify the cycle in such a way so that this compressor, or particularly the low pressure heat exchanger, operates below atmospheric pressure conditions. Because then only your temperature of low pressure side will be less in comparison to the temperature of the atmospheric condition or high pressure condition. All are clear to this point? So this type of cycle is called as sub-atmospheric reverse Brayton cycle. Okay, so what we need to do in sub-atmospheric reverse Brayton cycle? First point is very clear. It will be taking, compressor will be taking which air? Atmospheric air. Okay. Sorry, not compressor. We have to do the other way. Okay. So what will be happening? Let me tell you over here. So this is atmospheric air. This atmospheric air first will be passed through a heat exchanger. After that, it will be passed through turbine. Okay. So when it is passed through turbine, what will be happening? Its pressure will decrease. If it is entering at atmospheric pressure, here pressure will be lesser than atmospheric pressure. Now I will be having low pressure heat exchanger, in this low pressure heat exchanger, what will be happening? Its temperature will be slightly decreasing because it will be gaining the heat from the refrigerated space. Okay, from refrigerated space it will be gaining the heat. All are clear with this point? Then this air, partly I will be taking heat from refrigerated space and partly I will be taking the heat from this air to cool the atmosphere. And after that I will be passing it through a compressor. Now its pressure was lower than the pressure of atmosphere. Okay, so it will directly will not be going into the ambient condition. So in order to dump it into the ambient condition, I have to increase its pressure again to atmospheric pressure condition. So this compressor will be increasing the pressure to PATM condition, and again it will be dumping this air into the atmosphere. Okay, so in this cycle what I have done, I have actually replaced my high temperature heat exchanger. All are clear with this point? So high temperature heat exchanger is nothing but now open to atmosphere. All are agreeing to this point? So if high temperature heat exchanger is open to atmosphere, the refrigerated space has to be less than the atmospheric pressure condition. Then only temperature will go below the refrigeration, below the ambient temperature in an what? Open cycle. Okay, closed cycle it is easy to achieve, but open cycle this variation has to be done. Okay, so here you can see ambient air has entered at 1 point, it has cooled to 0.2 at atmospheric pressure, then its pressure has decreased to 0.3, partly it has gained the heat in the where refrigerated space heat exchanger, and partly heat gain is in this heat exchanger, and then it is again dumped to ambient. What will be TS diagram for this? Please tell me. This is my starting point 1. 1 to 2 I am having cooling, and both point 1 and 2 are lying on a constant pressure line which is at P atmosphere. Then 2 to 3 I am having expansion process. So then 3 to 4. 3 to 4 what is happening? Partly cooling at the low pressure. This is some pressure less than the atmospheric pressure. Then 4 to 5 is again some cooling in the, some heating, not cooling, some heating in the this heat exchanger, because T2 temperature is greater in comparison to T4 temperature. So heat will transfer from this side to this side, and then 5 to 1 again I have increased the pressure, and this here is again dumped to ambient. All are clear to this point? Anyone is having any doubts? So this type of cycle is called as subatmospheric reverse Breton cycle, and this is nothing but a open type cycle. What is process number 1 to 2? Isobaric, then 2 to 3 isentropic, then 3 to 5 again isobaric, 5 to 1 again. I am not joining this intentionally, though point is same, but I am not joining intentionally because it's an open cycle. Okay, all are clear with this point? This type of cycle is called as sub-atmospheric cycle. Okay, so sub-atmospheric cycles are majorly employed for gas, liquefaction, etc. Probably that is not part of our syllabus, so we will not discuss in detail. Now, next we will be studying about aircraft refrigeration or air conditioning system. Aircraft air conditioning system. Okay, so first you tell me why there is need for aircraft refrigeration system or air conditioning system. Why there is need of air conditioning in aircraft? Please tell me. But that heat is going into ambient temperature. Fuel is burned inside the engines, and engines are significantly away from the cabin, and that heat is directly dumped into the engine. For respiration, you need not to do air conditioning, you only need to do just circulation. For maintaining pressure, you again need not to do this air conditioning. You can simply use a blower or fan which can increase the pressure. Why there is need? For air quality, again you get fresh air from the ambient and keep on circulating it. Okay, first you tell me why there is need of air conditioning inside the room? To maintain the temperature. Why we need to maintain temperature? Just a simple question. For example, outside temperature is 22 and this is the room. In this room I have packed 200 people. So outside temperature is 22. It's a what? Human comfort condition. Of course, initially room temperature will also be 22. It's a human comfort condition. But now I have packed this room with 200 people. What will happen? Why temperature will increase? So first point is because of metabolism, body releases heat. Okay, so it means that whatever the persons who are sitting in the airplane, their population density is very large because the cabin of the that particular space of the aeroplane is very small, and in that small space we have put large number of passengers. So first point is population density is large. So because of large population density of occupants, we will be having heat generation. Okay, this heat generation will increase the what else? In the room, whenever this fan is rotating, it is doing some amount of shaft work on the air. So because of this internal energy of the air is increasing. Okay, so in the similar way, this is correct. You take an insulated room and perfectly insulated room, okay, and just keep the fan on. What will happen? Yes, because what you are doing? You are continuously adding electrical work. And that electrical work will be reflected in terms of increase in internal energy of the air molecules and ultimately temperature will increase. Okay. So we have tube lights etc. here. All these tube lights etc. what these will do? These are consuming electrical energy at certain rate. So it means these are generating some amount of heat. Okay. So we have different systems. For example, control system, electronic items, all these are the source of the heat generation. Then on aircraft, we also carry some amount of food items. So for preservation of the food items also we need refrigeration or air conditioning. Okay. What else? Now my next question is, at what height typically airplane flies? In the range, depending upon the type of the plane, but somewhere of the order of say 3 kilometers to 10 kilometers, 10 kilometers away. So if you go 10 kilometers away from the ground surface, what is the outside temperature? As we move in the stratosphere, as we move away from the ground, with altitude temperature keeps on decreasing. The equation for temperature is nothing but T equal to T naught minus beta into Z, where Z is actually our elevation. Okay. So beta is the rate at which temperature decreases with elevation. Okay. So this is nothing but degree Celsius per meter. All are clear with this point? Now, in stratosphere at 10 kilometers above the ground, where typically most of the plane flies, you will be finding temperature is close to minus 55 degrees Celsius. So even if there is any heat generation because of all these reasons, that heat should immediately gets dumped into the ambient. Then so we will not be requiring air conditioning. Why that heat does not go to ambient? Please tell me. When aeroplane flies, what happens? There is aeroplane flies at very high speed. There is relative motion in between the air and the plane. That relative motion will create boundary layer etc. on the plane surface, and even if Mach numbers are significantly greater than 1, then even there will be formation of shock waves etc. Okay. So what will be happening ultimately? Ultimately, at the body of the aeroplane, I will be having formation of boundary layer, which will lead to relative motion between the different fluid layers, and as these are having finite viscosity, so we will be having generation of heat due to viscous dissipation. Okay, so because aeroplane flies at very high speed, so heat generation due to viscous dissipation is significant. Okay, so now this heat generation will create a blanket of hot air across the body of the airplane. So this blanket of hot air will not allow heat to transfer from inside to the outside. But what will be happening? The temperature of this blanket is so high that there will be leakage of heat from outside air to the inside cabin. So in aeroplane there is some generation of heat even due to viscous dissipation. All are clear with this point or not? All are agreeing to this? So these are the different sources of heat generation within the cabin of the aircraft, which will lead to increase of temperature, and that's why we need to do actually air conditioning inside the airplane. Now, typically in aeroplane, we use air refrigeration systems. Now we need to justify what are the reasons for using air refrigeration systems. Why not use the vapor compression refrigeration system on an aeroplane? Please tell me some reasons why we go for air refrigeration system in aeroplane. Why not the vapor compression refrigeration system? What is vapor compression refrigeration system? The one which is used in our home ACs and domestic refrigerators. So why don't we use system like our home AC in aeroplane? Why we use air refrigeration system? Sorry?
In stratosphere, there is minus 55 degrees Celsius, the water may freeze vapor.
You can use other type of working fluid whose freezing point is because vapor compression does not mean always water. You can use any type of other working fluids. So what could be the reason? The first reason is, for operating air refrigeration system, what key components you require? Compressor and turbine. In your aircraft engine, we have a big compressor and big turbine already there. Okay, so already turbine and compressor is there. So it means that same compressor can be employed for even using the compressing the air for air refrigeration system. First point is that. So it means, however, if you use the vapor compression refrigeration system, then you need to use separate compressor, because for vapor compression system you have to use the compressor which can handle that particular medium. Okay, one point is clear. And weight is important parameter for aircraft refrigeration, because we need to decrease the weight. Okay, so we need not to put separate compressor. If we use air refrigeration system, we can simply use the compressor of the aircraft engine. Second important point is, whenever I am using the air refrigeration system, what I can do, once the air is cooled after the expansion process at the exit of turbine, that air directly I can dump into the cabin. I need not to use one additional heat exchanger for cooling the cabin. Okay, what I am trying to say is, for example, this is my cabin. So if I use vapor compression refrigeration system, then what will be happening? The cold vapors of refrigerant I cannot directly dump into the cabin, because these could be toxic, these could be flammable. So what I can do, I have to use then some heat exchanger over here, which will be having some coil, and over that I have to blow the air from the cabin, so that that air gets cooled. But in this scenario, if I use air refrigeration system, then after the turbine, I can directly dump the air into the cabin, and I can directly suck the air from some other point. Okay, so it means that weight of heat exchanger is also gone. I need not to use heat exchanger at the exit of the turbine. Okay. Other important point is, if I use some other refrigerant, that refrigerant can be toxic. So leakage of that refrigerant within the cabin can lead to what? If some toxic gas is leaking into the room, what will happen? It will not be good for human health. Okay, that can be flammable. It can catch fire. So on an aeroplane cabin, we need not to put anything which can actually has fire susceptibility. Okay, so all these are the reasons why air refrigeration is actually common in case of aircraft refrigeration systems. Now, what are different aircraft refrigeration systems or aircraft air conditioning system? To be more precise, because we are basically doing the conditioning of air. So there are 4 systems. One is called as simple aircraft air conditioning system or air conditioning cycle. Second is bootstrap aircraft air conditioning cycle. Third is regenerative aircraft air conditioning cycles, and fourth is sub-atmospheric aircraft air refrigeration cycle. Okay, so 4 different systems are used in the aircraft refrigeration, and each of these systems are used based on their characteristics and type of the aircraft. For example, for low speed aircrafts, we use simple aircraft conditioning cycle. For high speed aircrafts whose Mach number is greater than 1.7, we use bootstrap aircraft air conditioning cycle. So what are the reasons for that? That I will discuss in the next class.